Good morning. I am Abhirami. I am here to present our project EMG Signal Control Prosthetic Arm. So, the abstract of our project. The first and foremost aim of the project is to develop a prosthetic arm which can be directly controlled by EMG signals. These EMG signals can be collected using different techniques. One of the better technique is to capture it from the muscle surface using different muscle sensors. We are using myoware muscle sensor for our project. So the technique is electromyography. Electromyography is an electrodiagnostic medicine system for assessing and recording electrical activities. These collected EMG signals using the muscle sensors are processed and then employed to control the prosthetic arm. So this is the timeline. During the month of January, we analyzed different 3D models available for the robotic arm and fixed a suitable design which is simpler and easy to print. And we compared different motors that are available to drive the robotic arm. Mainly there were two motors, that are servo and stepper motor. Stepper motor provide high torque, but for our project it is not necessary. So, and servo motor is more economical and easy to use, so we decided to use servo motor. During the month of Feb, we interfaced the sensor with the servo motor, and we tried to rotate the servo motor. And during the month of March, we are doing the hardware implementation of our project. Almost the 50% of our hardware implementation is done, and the testing and validation is yet to be completed. So this is a simplified block diagram of our project. So the first and important block is the EMG sensor block. We are using a myoware muscle sensor in order to take the EMG signal from skin surface. The signal that is taken from the sensor is fed into a microcontroller, which is along with this sensor itself, which provide a proper signal processing and particular amplification that is needed to this particular signal, EMG signal. And in order to remove the noise and the noise in the signal, we are using an additional amplifier, which is an LM358 amplifier. And the signal that is amplified is directly provided to the Arduino. Particular threshold is already set up for each movement, and according to it, Arduino makes decisions and drives the servo motor attached to it. Servo motor actually drives the robotic arm.
Myself Aileen. So I'm going to discuss about the work plan. That is, I'm going to discuss about the first three phases. So in the first phase, actually what we did is that before implementing our hardware part, we made a detailed study and researches about the methods to be used. Then we also analyzed different kind of sensors to be used so that we can extract our EMG signal from our muscle surface. In this phase, we also analyze the different tools to be used, which includes our AutoCAD, different MATLAB. Such kind of tools were also analyzed in this phase. Again, we also made comparison with different sensors, and finally we came into a conclusion to use myoware EMG muscle sensor. So this sensor has got three surface electrodes, that is a positive, negative and the ground, so that you can see in the diagram. Then what we did is that we connected a microcontroller to the surface electrode. So the surface electrode basically gives analog output, that is by taking the signal from the muscle surface, and this microcontroller will convert this analog signal into digital form, and thus we also made moving on to our second phase. What we actually did is that we compared with our different motors available. That is, we basically went for servo motor and stepper motor and decided to use this servo motor. The servo motor that we used is Tower Pro MG90S mini digital servo motor. And the main reason that we use the servo motor is that it can provide a rotation of 180-degree, and this is the reason for which we used the servo motor, because the stepper motor has limitations in providing the rotations. And so this is basically a digital servo motor, and this can receive and process the signals much faster in a better way. So this is also a sophisticated internal circuitry, and this can provide good torque. It can hold more power, and it can also update to the external changes in the surroundings. So this is all about the servo motor that we used. Again, we also decided to fix a number of servo motors to be used, and finally we came into a conclusion to use 5 servo motors, basically to control our 5 fingers. That is the reason we use the 5 servo motors. Again, in the phase 2, we also analyzed the different 3D models of the prosthetic arm and finalized for a single design before our fabrication. So these are the main things we did in our phase 2. Next, moving on to our phase 3, what we actually did is that we inferred that our servo motor is basically controlled using the EMG signal via the Arduino. That is, Arduino is the main thing which can control our servo motor. And we also came into a conclusion, or we inferred that whatever variations are produced in the EMG signal, according to that, our servo motor was rotated each time. So these are the main things which we infer, and this is all about the phase 3.
This is Azin Sunny here, discussing about the discussion part in the PPT. So basically, the surface EMG signals are obtained from the limbs, and these signals are collected using EMG sensors. So in our right hand, we place these EMG sensors at 3 different positions. Basically, the muscles which control our right hand are together known as wrist flexor group. So this wrist flexor group of muscle, they contain 3 parts like flexor carpi radialis, palmaris longus, flexor carpi ulnaris. Now these 3 muscles together are known as wrist flexor group. So we place our sensor at 3 different positions, 2 at the end and beginning of this muscle group, that is the flexor group, and then the next one, that is the last one, acts as a ground, and it is placed at the side just before the knee. It is placed in the opposite side to that of the other 2 sensors. Now let me explain about the circuit diagram for EMG interfacing. The microcontroller used here is a 5-pin microcontroller. So there are 5 different pins. One is ground, one is for 3 volt, one is for output, then positive and minus. Now what we do here is that the ground of the microcontroller is connected to the ground of the Arduino. The 3 volt is again connected to the 3 volt in the microcontroller. Now we have the output, which is connected to A0 pin, that is the analog input pin of the Arduino. And our microcontroller consists of only 3 pins, that is the ground, 3 volt and output. So we are neglecting the case of plus or minus in this figure. Now this slide in the PPT represents the source code. That is the basic program that is used to interface the EMG sensor with Arduino so that we can view the direct live plot of the signal in our laptop using Arduino program. So as we all know, Arduino program consists of two parts. One is the preparation block and the execution block. So the preparation block is the setup part here. So it is just a preparation of the statements that we provide and that we have given here. And then we have the execution block where we repeatedly or our command goes in loop. So here we have sensor value is continuously read through the analog pin A0, and then we serially print the sensor value. Now the delay here is 10 millisecond. All the calculations in Arduino is in milliseconds. So this slide represents various tools used. First one is the EMG sensor kit. EMG sensor kit was purchased, and then we have Arduino Uno software, which is a very common software. All our programs were done in the software. Then we have Cura software. Cura software helps us to identify the time period which will be taken in order to print a particular part in 3D printing. So basically we need CAD drawings to in .stl format, and when we upload this .stl format, the kind of files into the Cura software, it will display the amount of time period in hours it will take in order to print it. Then we have FreeCAD and OpenCAD. We used these to check the dimensions and each size.
My name is Drishya. This is the timeline plan from 75%. It consists of 3 steps. First is assembling of 3D printed parts. Second is hardware implementation. And the third is testing and validating. So in assembling of 3D printed parts, we use screws and glue for fitting all these parts. If it is not fitting due to overhang, heat them slightly with a lighter flame to make them fit. Then coming to the hardware implementation, we will make a fully prosthetic hand with all the connections are made. That is, we connect all the motors and microcontroller to the 3D printed hand. Next is the testing and validating. So in this, after all the connections are made, we test it with an EMG signal. We try to rotate all the motors for the hand opening and close movement. If there is any error, we analyze and correct it, and again try to rotate the motors. Thus we complete an EMG controlled prosthetic hand. This is the timeline plan from 75%. Next is the contribution of members. First is Abhirami. She analyzed different 3D models, and from that we choose the CAD design of InMove. Also, she identified the specifications of EMG signal, waveform pattern and feature identification. Next is Aileen Maria. She finalized number of motors to be used in the robot hand. Here we are using total 5 motors. Also, she identified the different parts of InMove robot's arm. Third is Drishya PP. She compared the different motors and specifications. From that, we choose servo motor because it is more controllable than others. Also, she identified the various screws, strings to be used. Next is Azin Sunny. She is doing the interfacing of EMG signal with the servo motor and identification of InMove robot's arm with the different parts and structures. So, these are the contribution of members.
So, this is Azin back here to explain about the work that we have done up to 75%. So the first work or the major part that we have completed is the 3D printing part of the prosthetic arm, and this part is completed. We have different 3D printed parts of the robotic arm right now with us. We have to assemble it and do the connections necessarily, and then we'll complete it as a proper arm. Then we analyzed and fixed the number of servo motors to be used. Basically, we use one servo motor for one finger, so we have total 5 fingers, and therefore we have decided to use 5 servo motors. And we have analyzed the type of screws and threads to be used for the hardware design. So depending on the drill that we are using, or like the hole size, we have to purchase screws accordingly, and then the thread that is to be used is waxed nylon cord, which is easily available in the market, and it is comparatively inexpensive and appropriate for our use. Then comes the major part, that is interfacing the servo motor. So the signal taken from the EMG sensor will control the servo motor, like depending upon the value of the EMG signal, its variations, the servo motor will rotate particular angles. That is the main interfacing part that we have completed right now, and the source code for the same is mentioned below. So as discussed earlier, this Arduino program also consists of two parts. One is the preparation block and the other one is the execution block. So we first are explaining different pins that we have used. The sensor pin is A0, then we have servo pin which is 9, and we have defined a threshold as 680 because we have analyzed threshold for various individuals and we have come upon a single person's threshold variation in his EMG values were noted, and we have set the threshold accordingly. So 680 was the threshold, and then we have the rotation angles, that is one is 90 degree and then one is 170 degree. So the program is just a basic program. Now if the sensor value is less than the threshold value, then the servo motor will rotate up to an angle of 90 degree. That is shown in this slide. And if the sensor value is greater than the threshold, then the servo motor will rotate up to 170 degree. Else there will be a serial plot, a printing of error.
This is a CAD design of a prosthetic arm. It is a CAD design of a right hand. It is taken from InMove. So the right hand consists of total 18 parts. It is in .stl format. If any model we have to 3D print, it should be in .stl format. All parts print with an infill of about 30 to 40% and wall thickness 1.5 mm. Best with no support, no raft and no brim. These parts are connected using the screws and glue. The screws are chosen according to the hole size and accordingly purchased. Here we are using a waxed nylon cords for connecting the servo motor to the printed arm parts. Don't use standard nylon because it stretches. These are the references.
So that's all in overall. This is a 75% presentation. Thank you, sir. Thank you so much.